This is lesson 2 for chapter 16. If you look at the heading, electrical potential and potential energy, remember that the units for potential energy or any other kind of energy are joules, and electrical potential, which is volts. Electrical potential and potential energy are not the same thing. Volts is your potential energy per charge, the work done per charge. That work can be potential energy as you move a charged particle around in an electrical field. So this particular section is going to show you some example problems. And again, the trick is to keep in mind that you see the word potential used two different ways. One, the electric potential is measured in volts, and the other, its potential energy, which therefore means it's in joules. And the potential energy per charge is the volt. Excuse me. So, in electric circuits, a point of zero electric potential needs to be defined. When we talk about gravitational potential energy on the Earth, we usually think of the surface of the Earth as being zero potential energy. And that potential energy increases as you go farther and farther above the Earth. In terms of electrical potential, again, we think of the Earth as being zero electrical potential, and everything that is going to have a charge, we often have them grounded, which means they're connected to the Earth some way by means of a wire or a metal pipe or something like that. And we talk about the potential energy something has, or the electrical potential, I should say, that something has with respect to the Earth, which is defined as zero. The Earth is our sink for excessive charge. Now, just like a gravitational field extends out into space, so does an electrical field extend out into space. And just as gravitational potential energy extends out into space until it seems to approach zero, we could say that's when things seem to be weightless. The same is true for an electrical field. It extends out into space until its electrical potential can be taken as zero and an infinite distance away. Now, as we look at this next equation right here, remember that this comes from Coulomb's law, which we looked at earlier. Here's Coulomb's law right there. The force of attraction or repulsion equals some constant, a very carefully defined value of K, times the product of the two charges, and it's an inverse square law. Now, if I divide both sides by Q, then we get this equation right here. And remember that my force times distance is the same thing as work, and work divided by charge is the same thing as voltage. So don't want you to think that these equations don't have a derivation from somewhere. Now, if we come back and take a look at this graph right here, we have two curves, different slopes. Both of them have a negative slope. Both of them are therefore inversely proportional. But one is inversely proportional to the distance between the two objects, and the other is inversely proportional to the distance squared between the two objects. Where does this come from? Well, if you take this equation way back over here, you'll notice that you have a single r in the denominator because you multiplied both sides by r earlier on to derive this equation. And so that, when we graph it, looks like the line in blue. Down here, if we take Coulomb's law, and instead of multiplying both sides by r, we divide both sides by q, we get F over Q, and F over Q is the same thing as electrical field strength, and this is an inverse square law, and therefore this graph in red shows this relationship. And that explains why these two graphs in the same set of axes, as you go from 2 to 4 to 6 centimeters of separation, give you different slopes. Now, we've come across the superposition principle in a number of different contexts, in terms of sound and with amplitudes, in terms of light, and here in terms of electrical potential. And so you can have point charges in electrical fields, and you can have multiple sources of electrical fields, in which case you use the principle of superposition to find the total of the electrical field from those multiple sources at any point in space. Let's think of an electrical field made up of two charges. We would call this an electrical dipole, assuming the two charges are close enough to influence each other. Obviously, if you had two electrical point charges that are millions and millions of kilometers apart, for all intents and purposes, they have no effect on each other. You would not have what we would call an electric dipole. Now, in this graph, my ground, or zero, is right here, represented by this plane in blue. And let's say we have a positive charge located right in the zero plane, right below this red point. And let's suppose we have a negatively charged particle positioned right here, right above in the zero plane, this purple point. And along the y-axis, we have electric potential, in other words, voltage. And so we're making up the scale here, but let's suppose that if we are graphing the voltage from zero, the voltage from ground, it goes up to 2 with my positive charge, and it goes down to a negative 2 with my negative charge. And this is graphed in 3 dimensions, and it's color-coded, showing you what it would look like at 1/2, and at 1, and at 1.5, and at 2 volts. And then the same would be at -1/2, and -1, at -1.5, and at -2 volts, with respect to the ground, with respect to the zero plane, which is this rectangle that I've outlined in blue. You are actually going to be doing a lab that looks like this, or maybe you've already done it, where we're going to use a power supply, a 9-volt battery, which is going to have a positive and a negative, and we're going to have a tray that's going to have water in it and a grid, and we're going to actually create an electrical field, and we're going to measure that voltage at many, many different places in this field that's covered in water, and we're going to create a graph that's going to look very much like this. And if we have this pair of charges, charge 1, Q1, charge 2, Q2, obviously you have a certain amount of potential energy. This is Coulomb's law. And that potential energy would be attractive if Q1 and Q2 have opposite charges. If they have opposite charges, they are going to attract to each other because opposite charges attract. And by definition, a positive times a negative is going to give me a negative potential energy. If the two charges are the same, if they're both positive or they're both negative, when you multiply the two together, you're going to get a positive number for the product of my two charges. And so you're going to have a positive potential energy by this definition. So if we take a look at the next problem, I want to make sure I've got this correct and didn't skip anything. Here we go. So calculate the electric potential due to a collection of point charges. So here we have a 5 microcoulomb right there. that's positive, Q1, and we have a 2 microcoulomb right here, that's negative. And you'll notice that they are 3 centimeters apart. I'm sorry, it looks like these are 3 meters apart. 3 meters apart right there. And then if we, in part A, it says, if the electric potential is taken to be 0 at infinity, find the electric potential due to these point charges at point P with coordinates 0 and 4 meters. So this distance here is 4. Now hopefully right off the bat you recognize that this distance here therefore has to be 5 because we have a 3, 4, 5 triangle because this is a right angle right there. So with that information in place, we can calculate the electrical potential at point P due to the 5 microcoulomb charge. And that potential, measured in volts, is going to be my constant K. There's my K. And here's my Q1. And it's 4 meters below the point charge. And I get a positive voltage. Now, next, if we have the negative 2 microcoulomb charge, and it is located 5 meters from the point charge, that's the hypotenuse of the triangle, and here's my K. And of course, because it's negative, we're going to get a negative voltage at that place. These are 2 scalar quantities that the point charge is experiencing. And so we're simply going to add them together to get the total sum of the electric potential at point P as a result of the 5 and the 2 microcoulomb charges that have opposite charges. Now, when we want to find the work that's being done, remembering again that the definition of voltage is the work per unit charge. So therefore, my work is going to be my charge times the change in voltage. Q3 is that, it says find the work needed to bring the 4 microcoulomb charge from infinity down to P. So we take my 4 microcoulomb charge right there, we multiply it by the total potential as a result of the 2 charges in this field, and we get this much work that has to be done. Remember when we added these together right here, it's because they were scalars. We did not have to componentize any of the vectors. Let's look at another problem. Suppose 3 protons lie on the x-axis, and they're at rest relative to one another at a given instant in time. Obviously, being positive charges, they have to be held in position. And then at some point, charge number 3 is going to be released. We're going to take this charge right here, we're going to let go of it. It's no longer fixed in space, and as you can imagine, the direction that this positive charge would go is going to be to the right as it is being repelled by both Q1 and Q2. So when we go to look at the total work that the total potential energy that these charged particles have initially, I means initially here. First of all, we have the potential energy between charges 1 and 2. That's what R with a subscript 1, 2 means. It means R is the distance between charge 1 and charge 2. And R13 refers to the distance between charge 1 and charge 3. And R23 refers to the distance between charge 2 and charge 3. And so we're basically using Coulomb's law between charges 1 and 2, between charges 1 and 3, and between charges 2 and 3. They're all experiencing a repulsive force. That is initially. Now, when everything is said and done, and now we're going to look at the final, when Q3 has left, when Q3 is gone, it's now moving to the right. It does have a certain amount of kinetic energy, 1/2 mv squared, and the only potential energy that's left is the force of repulsion between Q1 and Q2. So initially, we've got 3 charged particles repelling each other. Finally, we have only 2 charged particles repelling each other, plus the kinetic energy of the third particle, which is now moving towards the right. So now when we come to use our work energy theory and add up the kinetic and the potential energy before, and which is going to be right here. Here's my total potential energy before, and here's my total potential energy plus kinetic energy afterwards. And notice that my distance between charged particles 1 and 3 is twice r. And that's where that came from. And notice that my potential energy that my third particle number 3 has, my kinetic energy that my other particles have is 0, because they're still fixed in place. And so here's my potential energy between the 2 particles. Neither particle 1 nor particle 2 have any more repulsive force repelling charged particle number 3 because it's left and gone to the right. So now when I simplify this expression down here, here is my final energy for my particle number 3 that's moving to the right. And I'm going to subtract the potential energy between my 2 particles from both sides. That goes over there. And here is the this potential energy right there. And now we get this expression. We can solve this for the velocity of particle number 3, and we can see that it is moving at less than the speed of light, but it's getting close. Again, the speed of light is 3 times 10 to the 8th. Now, section 16.3 basically is a bunch of statements about the surface charge density around an object. Excuse me. So, these statements should hopefully be kind of logical, that if we have an equipotential surface, this means that the potential energy any place along the surface of this object is the same. It's equal to any other place along the surface. And if all these potential energy places are the same, then no net work is required to move a charge between 2 points. All the charges have already moved to be in a position so that there's the work that's left to be done on any charged particle is now 0. And now you're at equilibrium. You have equipotential. Obviously, if you were not at 0, that means there was work left to be done on a charged particle. It would still need to move along the surface one way or the other, and you'd have a current along the surface until it reached a point that no work needed to be done anymore, because now the potential for any charge on the surface is the same as the potential for any other charge. So no net work is required to move a charge between 2 points when they have the same electric potential, equipotential. In other words, the voltage at any place is equal to the voltage at any other place. All points on the surface of a charged conductor in electrostatic equilibrium, and again, we're not talking about electrical current, that comes in chapter 17. We're talking about static electricity, a stationary charge. We have the same potential everywhere. Also, we can make this statement: the electric potential is a constant everywhere on the surface of a charged conductor. It's not 0, but it's the same value as at every other place. and the electric potential is constant everywhere inside the conductor and equal to the same value at the surface. Now we have a new unit of energy here that comes into play much more when we talk about nuclear physics, and that's called the electron volt. And when we talk about electron volts, we're going to be talking about the energies of, say, gamma ray photons, if you will, and X-rays. And we're going to talk about the values of these of the energy that these photons have per charge, and that would be measured in electron volts. So an electron volt is defined as the kinetic energy that an electron gains when it's accelerated through a potential difference of 1 volt. And when your particle is that small and that minuscule in mass, and it experiences a potential difference of 1 volt, we say that it now has the potential energy of 1 electron volt. And you can see that it's very, very, very small. It's very much like the charge of 1 electron. The charge of 1 electron is 1.6 times 10 to the minus 19th coulombs. And so if you take that charge and multiply it by a volt, which is the work per charge, you get this much work, 1.6 times 10 to the minus 19th joules. You're going to see that more when we start talking about energy values inside atoms, for example, in nuclear physics. Equipotential surfaces, again, all points of the same potential, means that this is an equipotential surface, and you have the same voltage everywhere. The potential energy difference is going to be 0. So there's no work that can be done or needs to be done. If you did any work on any charge, you would be actually forcing that charged particle to move in a direction that it would not naturally want to go, and you would be giving it a potential energy per charge. You would be increasing its potential. And if you let go, it would go back to its original equilibrium position. The electric field at every point of an equipotential surface is perpendicular to the surface. In other words, there is no horizontal component. It's all normal or perpendicular to the surface. After all, if you had a horizontal component, if this is my surface, and instead of my electrical field being that way, my electrical field was this way, then you would have a component along the surface, and the charged particle would move from there to some other position. And that's not happening. There is no movement of charge along the surface because there is no X component. The entire vector is moving normal, perpendicular to the surface. No matter what the contour is, your arrow representing the electrical field will be perpendicular to the tangent at that point in that curved surface. And these are called equipotentials, meaning equal potential energies per charge. Now you can see what this diagram would look like. And in a sense, what you're looking at is something like a topographical map. You might say, what if this were a mountain right here? And so this would be a place that has the same altitude. And then as you climb the mountain, you now reach a new altitude, and then a higher altitude, and then a higher altitude, and now you're on top of the mountain. This would be a topographical map that's measuring altitudes and depressions, mountains and valleys. And that would be for a uniform field around an electrical charge. If I have a dipole right here with a positive and negative, you can see that these dotted lines here are my equipotential surfaces. A couple of applications. The electrostatic precipitator. West of here, as the crow flies, I don't know, maybe about a half an hour, and when you get to the Missouri River, this side of the Missouri River, you have the Labadie coal power plant, and it burns coal. But coming out of the smokestack and this is not the Labadie coal power plant, but coming out of the smokestack, you see very, very, very little of this. And that's because of what we call an electrostatic precipitator that's giving all of this dust and ash particle a static charge. And when it has a static charge, that static charge is going to be attracted to a high voltage metal wire running down the center of this tube, and all of that powder, all that ash is going to collect, and then it's going to fall down here, and then we can haul all this dirt, all this ash, all this what would have been air pollutant, and we can put that in a landfill. So the dirty air comes in, and then the clean air goes out. An electrostatic precipitator. And coal-burning power plants have this. It used to be our air was very, very polluted in the vicinity of coal power plants. Back in the 1950s, there was a community south of Pittsburgh near some coal power plants where the pollution was so bad and there was so much particulate in the air that even in the middle of the day, you would have to put your headlights on in your car because the pollution blocked out the sun. And now, of course, our air is much, much, much cleaner as a result of this technology. There's also the electrostatic air cleaner, which you can buy for your house. Where my wife and I used to live in Kirkwood, I had terrible allergies, and our kids did, and we had to pay for an electrostatic air cleaner. And every now and then you'd hear a little spark as some piece of dust or pollen would get a static charge and be attracted to that little wire. And periodically I would have to empty or clean the electrostatic air cleaner, pull the box out and rinse it off with a hose to get rid of all the debris. And it was really difficult to do that because within days it would clog up again, and it was just tedious to have to clean our electrostatic air cleaner so often. There was an additional charge because every time you got this static charge that was released when your particle got zapped by the wire, it produced just a touch of ozone, and ozone turns out to be an allergen as well. Nowadays, we use physical filtration to get rid of dust and pollen as opposed to electrostatic precipitation. And we're going to stop there. You can read about the old-fashioned laser printers if you would like.